Assignment 2. Integrate 0 to infinity sine of x over x into x square plus a square dx is equal to pi over 2a square into 1 minus e the power negative a, where a is positive, strictly positive. Alright, so we will integrate fz is equal to, yes, I'm having sine x in the numerator, so I will write e the power iota z for the numerator, and then just replace x with z. So this is z into z square plus a square along C. And C is the contour consisting of the real axis. Just start from here, rho to r, and then the semicircle tau, and then from negative r to negative rho, the real axis, and then the semicircle gamma in the upper half plane from negative rho to positive rho, right? So first step is we have to find out the poles first. So just put denominator equal to 0, we get z equal to 0 and plus minus a iota. Now which of the poles lie on the real axis? Only z equal to 0, right? So on the real axis I'm having the pole z equal to 0 here. So we are going to make the indent only on 0, right? And plus minus a iota. Which pole lie inside the contour? Of course, a iota lie inside the contour and negative a iota lies outside the contour, but not on the real axis. Alright, so for the three poles, I'm having the indent only for z equal to 0, and for z equal to a iota, because it is lying inside the contour, we are going to find the residue for this pole. Alright. So let's find the residue of fz at ai. Just like we have just find out so many residues in the previous videos, same steps we are going to follow. Okay, so residue of fz at ai is equal to, just write the numerator as it is, which is, just write e the power iota z over z, and then derivate the denominator with respect to z, z square plus a square at z equal to a iota, and then this is equal to e the power iota z over z divided by, this is 2z, at z is equal to a iota, and then just put the value of z over here, you get e the power negative a, because iota square is negative, over 2a square with negative sign. And now next step is I have to use the Cauchy residue theorem, which is the integral over whole contour fz dz is equal to 2 pi iota times the sum of the residues, because I'm having only the one residue. So 2 pi iota times the calculated residue. So this is 2 pi iota times e the power negative a over negative 2a square. 2 will be cancelled with 2, and then we are having finally negative pi iota over a square e the power negative a. And now just let's split up this contour C in the 4 parts, right? First is from rho to r, right? And because it is on the real axis, so the contour is along the real axis, so I'm writing f of x dx. And then the semicircle tau in the upper half plane, for that I have to use fz dz. And then again I'm having the real axis from negative r to negative rho, this is negative rho, and this is f of x dx, and then the semicircle gamma, and for that I'm writing fz dz is equal to minus pi iota over a square e the power negative a. Now since 1 over z into z square plus a square is tending to 0 uniformly as z tends to infinity, and this is your meromorphic function in the upper half plane, so by Jordan's lemma this integral is 0. So the limit r is tending to infinity, integral over this tau fz dz is equal to 0. And now calculating for the gamma, right, for this. So limit, now for the gamma, for gamma semicircle, I have to limit the radius to 0, right? For tau, I have to limit the radius to infinity. For gamma, I have to limit the radius to 0. So limit rho tends to 0, where rho is the radius of the semicircle gamma, fz dz integral is equal to, the formula is iota last angle minus the first angle, and it is always 0 minus pi in every question, right? So the last angle is 0 and the first angle is pi. So it is always iota into 0 minus pi. Limit z is tending to, what is the pole? It is 0 into z minus 0 f of z. For any pole A, the formula is limit z tending to A into z minus A f of z, because here A is equal to 0, the pole. So it is limit z tends to 0, z minus 0 f of z. So this is equal to negative pi iota limit z is tending to 0 e the power iota z over z square plus a square. So this is equal to negative pi iota 1 over, just put z equal to 0 over here, this is 1 over a square. Here a is another variable, right? Here just you look at her, I'm having already a square in the denominator. This is another thing, and I'm talking about the pole z is equal to a is the another thing, right? So you can also just say, as because I'm already having a for the function fz, you can write limit z tends to z naught, where z naught is the pole, right? Where z naught is equal to 0. Please don't confuse. So next it is, now because I have calculated the integral for both the semicircles, so for the equation 1, for this equation I have to limit r tending to infinity and rho tending to 0. So letting r tending to infinity and rho tending to 0 in 1, we get for rho 0 and r infinity, so first integral will be from 0 to infinity. F of x dx, and then this is 0, right? The third one is negative infinity to negative 0, and negative 0 is simply 0. So this is negative infinity to 0, f of x dx, plus for the last gamma I am having simply fz dz. E raised to the power negative a. And because I have already calculated the value for this, so I am putting this value over here. So this is, and I'm just merging these two. This is from negative infinity to infinity f of x dx plus the value, it is negative pi iota. So this is minus pi iota over a square is equal to minus pi iota over a square e the power negative a. Fine. Just take this to the other side. I will get minus infinity to infinity f of x dx is equal to pi iota over a square minus pi iota over a square e the power minus a. Writing the next step here only. Just take pi iota over a square common. So this is pi iota over a square into 1 minus e the power negative a. Right? Okay, because I'm having iota here and f of x is what? Just write f of x here first. The value, which is e the power iota x over x into x square plus a square. So just simply equating the imaginary parts, right? E the power iota x is cos of x plus iota sine of x. If I equate the imaginary parts, so I'm having sine of x in the numerator. So equating the imaginary parts, I'm having negative infinity to infinity sine of x in the numerator, denominator as it is, dx is equal to pi over a square 1 minus e the power negative a. Reason, e the power iota x is equal to cos x plus iota times sine of x. And because this is your even function, right? So the integral will be changed to twice 0 to infinity sine of x over x into x square plus a square dx is equal to pi over a square 1 minus e the power negative a. And then taking 2 to the denominator. Alright, fine. So this we have now proved. The result is now being proved. Thank you so much for watching this video.